strong duality theory. Next, since we are minimizing our primal objective function and we are trying to maximizing my dual objective function, so during the solution, during the solution process, I'm keep minimizing my primal objective function and keep maximizing my dual objective function until they reach to the optimal objective function value. They becomes zero, becomes equal, and then this is the optimal solution. Look at the objective function value equal to C transpose times X, and equal to CB transpose times XB, and CN transpose times XN. So CB is the cost coefficient for the basic matrix times the basic variable times the basic variable, and CN represents the cost coefficient corresponding to the non-basic variable times the non-basic variable. However, we know X non-basic variable are currently equal to 0, so they cancel out. So therefore, the solution will be CB transpose times B inverse times B, because XB equal to B inverse times B for now. And CB transpose and times B inverse, we know that is omega. We define it as omega. So equals to B transpose times omega. Column 1 showed me if X and omega are feasible solution for both primal and dual respectively, with C transpose times X equal to B transpose times omega, then both of them are currently optimal feasible solution. When they're optimal, these two value, objective function value, will equals to each other. Category 2, if either one of the problem has an unbounded solution or unbounded objective function, then the other problem, corresponding problem, has no solutions of infeasible problem. We're going to summarize this in the next slide. We call the fundamental dual theory. Given primal and dual problem, one of those following statements has to be true. Okay, which means three of the conditions in our primal and dual problem relationship. First is both have optimal solution X star and Y omega star, and C transpose times X star equals to B transpose times omega star. Second, if one of the problem has unbounded objective function value, then the other one is an infeasible problem. There's no feasible solution for the dual problem, or the other way around. The third condition may happen is both problems are infeasible problem. Okay. Here we have primal problem, and here we're talking about complementary slackness condition. Here our primal problem looks like minimize of a C transpose times X, AX greater than or equal to B, and X is greater than 0. And for the dual problem is maximization problem with a B transpose times omega, and subject to A transpose times omega less than or equal to B, and omega are non-negative. And also, we say that the U represents the primal surplus variable, and the V represents the dual slack variable. The theorem states if X and omega are the feasible solution for primal and dual problem, we presented here respectively, and then the the following equation has to be whole, and this we call a complementary slackness condition. And using two English sentences easily describe this, so it's probably easier for you to remember. The dual solution times the primal constraint equals to 0. Primal variable times the dual constraint equals to 0. This is a very major result from duality theory, and later on using the primal feasibility and dual feasibility plus the complementary slackness establish the so-called optimality condition for optimization problem. It's applied for linear programming problem, applied for nonlinear programming problem as well, and it's a very important result for defining an optimality condition, which means your current solution is optimal. So it is a so-called stopping criteria for any algorithm exists. First, we know from the primal problem, okay, U equals to AX minus B, A times X minus B is non-negative. And we also know omega is non-negative. So omega times U is greater than or equals to 0 for all the omega. And also omega transpose times U is greater than or equal to 0 in that case. So what if now omega transpose times U for equal to 0 for all of the situation at the optimal. Also, for X and omega are the feasible solution currently for primal and dual problem respectively. I can have omega times AX minus B equals to 0, okay, and that's one of the results. If omega is greater than 0, and that means omega I is currently a basic dual solution, and then corresponding to AI times X minus BI will be tie, which is equality situation whole instead of less than or equal to. Okay, if the equality condition didn't hold and AX is greater than or equal to BI, and then that means the corresponding dual variable has to take a value of 0. Likewise, we can prove it to X. Okay, the X is transpose times A transpose times omega minus C equal to 0, because, and this is my also, we're trying to conclude xj times vj. Vj is the dual slack variable. So primal variable times the dual slack equal to 0. Here what we have is what? Dual variable times the primal subclass equal to 0. Okay, this is our conclusion. So here what we have, if x is greater than 0, means x is a basic variable, then the corresponding dual constraint holds an equality condition. And there also means the dual slack equal to 0. Since this is a holding for, this is less than or equal to constraint over here. If that equality condition holds, that means the slack variable equals to 0, and therefore, and also means the zj minus cj equal to 0. If the inequality condition holds, which means AJ transpose times omega is strictly less than CJ, therefore the dual slack variable is greater than 0, and therefore ZJ minus CJ is less than or equal to 0, and that means the corresponding XJ is a non-basic variable, and therefore it equals to 0. Two summary for this result. First, positive variable in one problem, meaning what? Tie constraint in the other problem. Okay, this is a summary, takeaway, message. Second, constraint not tie in one problem means the 0 variable, non-basic variable in the other problem. Okay, so here we're going to here we're just trying to see so-called the due problem. The due problem of the due problem is the primal problem. It's a fairly straightforward proof. So if I have a due problem is a maximization of a B, maximizing B transpose times omega, and subject to A transpose times omega less than equal to C, and omega is non-negative, and is corresponding, we can, since it's less than equals to constraint, we can convert it to greater than equal to constraint, and also convert a maximization problem into a minimization problem, so that we have the same format like the original primal problem to begin with. Then the corresponding due problem of this problem will be actually maximization of a negative C transpose times Z, and also negative A transpose times Z is less than equal to negative B, and Z is non-negative. And if I here, since I have a negative C, I can convert this back into minimization problem, and since I have negative on both sides, then I can multiply another -1 to turn this less than equal to constraint into the greater than equal to constraint. So therefore, I come up with a minimization problem, greater than equal to constraint, non-negative the constraint on the variable, and that's the original primal problem. Okay. So here we're trying to understand, we call which one is the primal problem, which one is the due problem, is a matter of convenience. We can start with any form and follow this transformation and write it out, the corresponding due problem. All right. For example, what if now we're trying to generalize our result? For example, what if our primal problem is an equality constraint instead of a greater than equal to constraint? What's going to happen? So if it's an equality constraint, then we convert this into two parts. We can convert both of them to greater than equals to constraint. So AX greater than B, and negative AX is greater than negative B. Okay, so separate them out to two equality constraints. Actually, this also means AX equal to B. So therefore, our constraint matrix will be A and negative A times X greater than B and negative V. And then we can corresponding due problem equals to mu and v, U and V. So B transpose, right here, B transpose and B inverse transpose. So B transpose times U and negative B transpose times V. Same thing, 90-degree turnaround for the constraint matrix. So A transpose and negative A transpose times U and V is less than or equal to C, and U and V are non-negative. So we can actually continue to simplify it, and it becomes a maximization problem with B times mu, U minus V, and A transpose times U minus V less than or equal to C. Both U and V are non-negative. So therefore, summarize them together, these two together. So we're assuming omega, do a variable transform, the omega equals to U minus V, and therefore, actually, the omega itself is unrestricted. So it can be a positive value or negative value. So this particular slide tells me if it's an equality constraint in the primal, and the corresponding due problem is unrestricted. Okay? So now we have two results. First, if the primal problem, minimization problem, it is greater than or equals to constraint, the corresponding due constraint, due variable is non-negative. If a primal constraint is equality constraint, my due variable is unrestricted, can take any value. We further generalize this result. Okay, what if I have greater than equal to constraint, equal to constraint, and less than equal to constraint? So the corresponding due variable, if I have a greater than equals to constraint in the primal, and the corresponding due variable will be non-negative. If I have an equality constraint, the corresponding due variable will be unrestricted, can be negative or positive. If I have less than or equals to constraint in the primal, then my corresponding due variable will be non-positive. Okay, it's a negative or 0. Due problem as well. For this problem, the corresponding due problem becomes B1 transpose times omega 1, B2 transpose times omega 2, and B3 transpose times omega 3. And our constraint turn 90 degrees for A1, A2, and A3. A1 transpose times omega 1 plus A2 transpose times omega 2 plus A3 transpose times omega 3, and less than equals to C. Okay, omega 1 is non-negative, omega 2 unrestricted, omega 3 are non-positive. Since this is less than equals to constraint, and the primal variable is non-negative as well. All right. This slide, I make a table for all these relationships summarized in the table. So for your safekeeping and reference, this table is much easier. I didn't specify which side of the table is primal or due. So if this is a primal, that's a due. If this is the primal, and that's going to be your due. Here I separate into a so-called, on the top portion, here is the variable and corresponding to the due constraint. Primal constraint is going to corresponding to the due variable, for example. All right, or the other way around. Let's read this real quick. For your primal problem, it's a minimization problem, for example, this one. If your primal problem is this one, for example, I can have a primal problem on either side. If your primal problem is on the left-hand side, if your variable has a non-negativity constraint, and then your corresponding your primal variable is non-negative, then your due constraint is less than equals to constraint. Okay, on this side. If your primal variable is non-positive, then your corresponding due constraint will be greater than equals to constraint. If your primal variable is unrestricted, then in your due you will have equality constraint. Same thing. Look at the primal constraint side. If you have a greater than equals to constraint, your corresponding due variable will be non-negative. If your primal constraint is less than equal to constraint, then your corresponding due variable will be non-positive constraint. Okay, non-positive constraint. If you have an equality constraint in the primal, then you have unrestricted due variable value. Okay, so here is the interpretation of the due variable. For example, my primal problem is the maximization problem. Okay, and C transpose times X, and I have AX is greater than or equal to B, X is non-negative. So look at the optimal solution. For example, I have XB and 0. 0 is the non-basic portion. And Z hat, which is the objective function, equal to CB transpose times XB, since Cn is 0. So equal to CB transpose times B inverse times B. And we know that CB transpose times B inverse equals to omega. And equals to B transpose times omega. So that's what it is. All right. And this is what let's do that. So this is what we're trying to do. If we relax B on the right hand side, the BI on the right hand side for each one of them, and then I can change my objective function gradually over this. So that means what? For Z, actually, right here, for your objective function over the each one of your right hand side, we call the so-called shadow value for that particular constraint, it will be omega I. Okay, so keep relaxing the right hand side, which means make resources more available. You can gradually improve your objective function, since your objective function is a maximization problem. If it's a minimization problem, this curve will be going downward like that.
You're at 21 minutes from now.
Okay, we continue this lecture with the next video.